Okay, we are finding the moment of inertia of a uniform ring of mass m and radius r around its center. So we'll imagine we have a z-axis, an x-axis, a y-axis, and we'll put the ring inside of the xy axis. So it will be rotating around its center at z. Okay. So the distance out here will be r. We're going to look at sort of a projection for our ring. Let's locate the center right here. We're going to look for a little piece of mass. We're going to say that little piece of mass is this shape right here. That's our dm. Notice it is an arc of length ds, where we have r along the side and d theta along the middle. So ds is r d theta. Let's see, this is actually a linear problem. So we have m over the total length, which will be mass over 2 pi r, and that will be equal to dm over dl, where that is going to be in our case dm over ds. So dm will be m over 2 pi r times r d theta, or if you cancel out the capital R, m over 2 pi d theta. Now notice, every piece along here, every dm, is the same distance away from the center. It's always capital R. So when we go to set up our integral r squared dm, we're going to have it just be capital R. It's always a distance big R, the radius of the ring away. dm, that'll give us m over 2 pi d theta. How much will we have to go around? Well, we have to start at some point and go all the way around until we get back. So that will be from 0 to 2 pi. Most of this is constant, so we can pull it out in front. We get an integral over 0 to 2 pi d theta, and we get mr squared over the 2 pi r constants times the result of our integral 2 pi. We get mr squared. And note, same I as a point mass. So the moment of inertia of a point mass that we found last time, well, before the rod actually, so a little bit more back than that, back when we first talked about rotational kinetic energy, the moment of inertia of a point mass is just mr squared, and so it is for a ring. But that actually makes a lot of sense if you think about sort of that stretch principle. So you can imagine that point has just been smeared out into the entire circle to make the ring. So it actually does make a lot of sense that the ring and the point mass would have the same result, mr squared. All right, that's actually it for this one. So 3.5 minutes, not bad. We're going to handle the disk next. We're going to do it without double integrals, and then we'll come back and try some other stuff.